All right, we're going to take a look at another method for Riemann sums. This is going to be the trapezoid method. You can see right off the bat that if we were to draw some trapezoids around this graph, we have very little gaps between these trapezoids in the graph. So it looks way more accurate than some of the other methods we looked at. For example, the last method we looked at, midpoint, we had some gaps right here, and we had some overlap. With trapezoids, we want to try to avoid that by getting as close to the curve as possible. And yet again, the more trapezoids we draw, the closer the approximation is going to be. Those lines are going to fit the curve better as we draw more trapezoids. Now, as I said, for right now, we're just going to talk about total area. We're going to assume that all of these trapezoids have a positive area. Later on, when we talk about the definite interval, we'll talk about net area, meaning all these trapezoids below the x-axis will take on a negative area, all the ones above will take on a positive. So why the trapezoid method? Well, again, they tend to be closer to the curve of the graph than, say, a rectangle. Now, the real question is, how do you figure out these areas? Well, we're going to do the conceptual way first, and then we're going to do the practical quick way next. So who remembers the area of a trapezoid? Well, let's just look at this first trapezoid we drew from -2 to -1.5. Now you can see the width of these is going to be the same as the width of the rectangles we did in these other ones. So they're going to be 1/2. The difference is that for a trapezoid, the heights vary. So at -2, we'll go all the way down to the graph and draw a point. But we're going to do the same thing for -1.5. Go all the way down to the graph and draw a point. When we connect these 2 points down at the bottom, combine with these 2 points up here and make a quadrilateral, it ends up being a trapezoid. Now the next one is a triangle, okay? When we connect these two, there is no height for this at -1, so it ends up being a rectangle. Okay, so it is the trapezoid method. However, sometimes your second height is 0, so it ends up being a triangle, which is fine because it still hugs the graph very well. Okay, much better than a rectangle. But overall, for the most part, they will be trapezoids provided the two x values yield an actual height or an actual y value other than 0. So what is the total area? Again, I'm going to underline that. I like to teach total area first before net area. Net area is definite interval, which is what we're ultimately trying to get to. But to me, total area just makes more sense because in the real world, most of the time, the area of something is always going to be positive. Okay, so what's the total area between the curve of this function and the x-axis on the interval -2 to 2? First of all, we'll talk about the conceptual way. The area of all these trapezoids, and I should say total area, so let me stipulate. Alright, so the total area of all these trapezoids is going to be 1/2 height, b1 plus b2. And we're going to take the absolute value to find total area. If it was net area, we would not include the absolute value bars, which we would talk about in a future lesson. Now, here's the thing. The height of each of these trapezoids is actually just going to be the same as the width of your rectangles, which is determined by taking the difference between your two x values. Here's what I mean. The height of this first trapezoid is just 1/2, the difference between your x values, okay? Your different bases, okay, are determined by your two different y values, hence y1 plus y2. So we're substituting y1 and y2 in for our base 1 and base 2, meaning these two bases right here, whereas the height of these trapezoids is determined by your change in x. Now in this case, it's always going to be 1/2, just because we determine we might as well make it the same as our width of our rectangle. So it's a little confusing just because it doesn't look like height because you're looking at it, from the top of the graph. But if you kind of look at it sideways, you can see it's the height of that trapezoid. So your height's change in x. The different bases are determined by your different y values. First trapezoid, you're going to have two 1/2s in this case because it is 1/2 h b1 plus b2. So it would be 1/2 times the height, and then your two different y values are determined by -2 and -1.5. Okay, so here's your first y value, and then you're going to be adding your second y value, which is determined by plugging in negative 1.5 into the function. So it's a pretty complicated formula, but at the end of the day, you get 1.0625. So the area of this first trapezoid is 1.0625. We can use a similar format, a similar pattern to determine the area of our next trapezoid, 1/2 times the height, which is still 1/2. So 1/2 times 1/2. And then you will multiply that by the two y values. Now your first y value is down here. It's actually the same y value that you used for your B1. So your B1 of your first trapezoid is going to be, I'm sorry, the B2, your base 2 of the first trapezoid, so we're talking about right here, whatever that y value is going to be the same as B1 of your next trapezoid. In this case, it's a triangle. But that will always be the case. They share. So for example, like this trapezoid, these two trapezoids right here, okay? The second base of this trapezoid right here is the same as the first base of this trapezoid. So they will always share that just because it's the same exact y value occurring twice. Now, that will happen for all the trapezoids except for, if you notice, like the base 1 of the first trapezoid, it doesn't share with any others because it's the leftmost. Same goes for base 2 of your last trapezoid. It will not share with any other trapezoids. So your second trapezoid, 1/2 times the height times base 1 plus base 2 equals 0.3125. So the area of this little triangle is 0.3125. Next trapezoid would be 1/2 times the height, which again is just 1/2, times B1 plus B2. Again, in this case, B1 is 0. B2 you will find by plugging in negative 0.5 into this equation, taking the absolute value for total area. You add those two bases up, multiply by that 1/2 times the height, and you get 0.1875. So this triangle is very small, 0.1875. And you will continue and find the area of the rest of your trapezoids. It makes sense that the ones in the middle are the same. You can look at them and tell that they are the same thing reflected over the y-axis. Add up all of these heights, all of these areas, because we've already multiplied by their the height, or if you want to talk about the width of these trapezoids, same thing. Add up all of these areas of the trapezoids, and we get 4 again. The same exact number we keep getting for all of our methods. Now, like I said, that usually doesn't happen. I like to do it for this example at least because it's symmetrical. It kind of confirms that each of these have their own strengths and weaknesses. I do like the trapezoid method though because it hugs so closely to the curve. But now what we want to talk about is how do we do the trapezoid method the quick and easy way without having to draw the graph every time. What is the total area of this function? Again, total area, a good way of relating that to the real world is if you are running around a track 4 times, you will run a mile in the US, right? Now you do end up where you started, but the total distance that you traveled is a mile. This is the similarity with total area, okay? It correlates where we make all of these areas positive. When we talk about the definite integral, we will talk about net area, which is assuming that the trapezoids below the x-axis are negative. So determine the interval length. It goes from -2 to 2, so it's 4, just like the rest of ours. We're still going to use 8 shapes, in this case 8 trapezoids, like we did with our left, right, and midpoint approximations. We will use 8 trapezoids. Again, the more the better. So if we use 16 trapezoids, you can imagine how different that would look, but it would be closer to the curve of this graph and hence more accurate. Step 3, we're going to determine the width of the trapezoids. You take your interval length and divide by the number of trapezoids, and you can see it's 1/2, and visually that makes sense. The width of these, or if you plug into the formula, we actually call it the height. It's whatever the bases aren't, right? So think of it as width or height. The width of these is going to be 1/2, or call it. Determine the x values of each trapezoid. When you're doing trapezoid, you have to use all x values. So everything from -2, when -1.5, -1, -0.5, 0.51, 1.5, and 2. You do have to end up using all of them. Now, as I said before, your left and rightmost values are only used once to determine the, your different bases of your trapezoids. But starting with your first and second trapezoid, they share a common base. So that base will occur twice. This is going to happen every single time for all these trapezoids in the middle. Okay? So think about that as you do the shortcut for trapezoids. You only use your left and rightmost x value once for your bases. All the ones in between are used twice. Step 5, determine the heights of the trapezoids. Plug in all the x values into the function and take the absolute value. Again, this is for total area. If you were finding net area, you would not take the absolute value. You would just consider their heights negative. So we will plug in all of these x values to get all of these different heights, and basically what that gives you, what it gives you is the base lengths of each of these trapezoids. Okay, start at 3, then we go to, let's see, what's the next one? 1.25. So this one is 1.25, then we get 0, obviously, and the next one that we get is 0.75, and so on and so forth. Next one's 1, obviously, and then it actually repeats, right, because it's symmetrical in this case. But like I said, the first and the last height you only use once. The ones in the middle you use twice, which I've notated with this blue line right here, this blue brace. These we use twice for our bases. So we go to do our formula, we add up all of the middle heights and double them. Then we add the first and last height since they only occur once. So here's the thing. If you add these middle heights up, 1.25 plus 0.75, that's 2. Plus 1 is 3. Plus 0.75 is 3.75. Plus 1.25 is 5. But since they all occur twice, since each of these trapezoids in the middle share a common base, you will take that number 5 and you will double it to get 10. Now, because these outside bases only occur once, you only add those once. So you take 10 and add 3 and 3 to get 16. That gives you all of the base measurements for each of these trapezoids. Now, because they all have the same common width, I can do the same thing with the rectangles and pull that common width, or if you want to call it height, of each of these trapezoids out, and whatever I got for all of my bases added up, I can multiply by that height or width of each of those trapezoids. So take the 16, all of the bases added up, multiply by 1/2. Now, the area of a trapezoid, however, also for the formula involves a 1/2 at the beginning. So it's 1/2 times the height of all of these trapezoids times all of their bases added together. So basically what you're doing is you're pulling out a 1/2 h for each of these, and once you add up all of the bases, then you multiply by that 1/2 h. So after you've doubled all the ones in the middle and added the ones on the outside, 3 and 3, so you get 16, you multiply by 1/2 h. Now h is not always going to be 1/2, right? For example, had we chosen only 4 trapezoids, the height of each of these would have been 1, so we would have multiplied by 1/2 times 1. But in this case, it happens to be 1/2 as well, so it'll be 16 times 1/2 times 1/2, which gives you 4 again. So we actually get the same exact approximation for our other methods. Again, that usually doesn't happen, but kind of illustrates that each has their strengths and weaknesses as far as each method goes. That's it for the trapezoid method. Again, we are approximating the total area right now using Riemann sums. I like the trapezoid method again because it tends to fit the curve of the graph better than the left, right, or midpoint approximations. If you have any other questions about this method, let me know.